All right, ladies and gentlemen, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Stop by the deli. Make yourself a smoked ham and peppered turkey sandwich with American cheese on a good old-fashioned Klosterman's honey bun with yellow mustard and pickles. All right. We are into Chapter 11. Welcome. Hope everyone enjoyed Chapter 10. We're now talking about vector-valued functions, okay? Often we're going to call these in terms of t because it's going to be very nice for us to consider our parameter, all right? Our parameter as a function of time. And that's what turns these into parametric functions. So, often in two-space, you will see it written like this. R of t equals f of ti plus g of t j. So wholly variable Batman. So what are we talking about? All right, we're talking about a general, okay, plane curve. And for a plane curve, we assign a vector. So we can also write it like this, at different times t. So as t changes, our actual functions that determine our vector change, okay? And so in 3-space, we can write this r of t equals f of ti plus g of tj, a f g h plus h of t I j k. Holy smokes. Or we will write that as f of t comma g of t comma h of t. Well, luckily you're only watching this if you're a good student, because those of you that are not good students probably aren't watching this. And so if you're watching this, you're going to stick with this because you're probably very intimidated by these things. Don't be, okay? Don't be intimidated by notation as you move on in math and science. It's just different than what you're used to. You're going to understand this. So let's try this. Let's look. This is a vector-valued function, okay? So now we have an input-output chart that looks a little different. We have t, and then we have I, and we have j, and then we have our vector. So look, at t equals 0, our I is 0, our j is 1, so our vector is 0, 1. At t equals pi over 3, our I is 1/2, our j is radical 3 over 2, and our vector value is 1/2, comma, radical 3 over 2, okay? Let's do this. Pi over 2. We got rad 2 over 2. Oh gosh. I swear I'll be done soon. Joinks. Okay, and then okay, so look, you can see that as our t goes from 0 to pi over 2, okay, our vector value function starts here with this vector, and then it moves on to this vector, and then that one, and then that one, and then that one. I mean, I think you guys understood what this was going to look like. Okay? Now, let me explain to you what a vector-valued function actually is doing. The plane curve is the graph of all of the endpoints of the vectors. Okay? So you guys know that this graph is going to be a circle. But now our plane curve traces the endpoints of vectors as t is changing. So one of the biggest difference between a typical graph, which is a circle, and a plane curve is that it is important to notate the orientation of the curve. Okay, so notice this has a counterclockwise orientation, meaning as t increases in the positive direction, this is where particles are moving on the curve. Okay? Now, I'm not going to write out all of those same examples because I feel like I've already probably lost half of you guys that are watching this video. But if I had the negative version of that, okay, all that would change would be, this would be 0, -1, and this would be -1/2, comma, negative radical 3/2. And you could imagine that this curve would start, our first point would be there, and then here, and then there, and then there, and so it's, and then look, so now you can see visually the difference. Assume these have the same unit between those two functions. Okay, the exact same curve. I'm so ashamed of this curve. It makes me kind of want to cry, but there you go. The exact same curve with different orientation. Okay, so now you're hopefully more comfortable with that term orientation. Okay, so now let's try to graph two space curves at once. Okay, space curves, how are they different than plane curves? Well, they have an I, a J, and a K. Notice I wrote these in a different format. Okay, so let's at T. Now let's have R of T here, and then we'll have R of T in red, and let's have our S of T here in blue, and let's just pick some even easier values for T. Let's go 0 degrees, switching back to degrees now, 90, 180, 270, oh geez, oh Pete's, sure, 360, and 450, and 540, and 720. Okay, so here R of T sign comes first, so it's 0, 1, 0, and then 1, 0, 90. All right, let's get this right so we can get the pattern right. And then 0, -1, 180, and then -1, 0, 270. Okay, so you can imagine that. Now the blue one. Okay, cosine of 0 is 1, 0, 0. Cosine of 90 is 0, 1, 90, sorry. Cosine of 180 is -1. And then cosine of 270 is 0, sine is -1. Okay, alright, so check this out. Remember, when we graph space curves, we're only graphing the end of the endpoint. Our z-axis has to go up by 90s. I mean, it doesn't have to, but that makes it nice. Okay. All we need on the bottom is enough room for the unit circle. Okay, so we'll have a little 1, 1. Uh-oh. Okay, so let's write. Alright, so what we're going to have here, our first point on our red one, will be 0 in the x, 1 in the y. Okay, now this thing is going to be growing up the side of this cylinder. Now this cylinder would be dashed in the back. Okay. Alright, so let's start with the red curve. It's got this point. It's got the point 1, 0, 90. So it comes up to here. It's got the point 0, negative 1, 180. Okay, and then it's got the point negative 1. Sorry, I just put this in the wrong spot. Negative 1, 0, 180 would be here. This is 0, negative 1, 180, and then negative 1, 0, 270 is going to be up here. And you can maybe picture this like that. Okay? Now the blue one, and then here it's going to start climbing again. The blue one starts here. And it's going to climb in a parallel fashion like this. So you can kind of think of that like one of these spinning barbershop poles. Or if we changed this to like a negative sign, if we had t of t, and we did negative sine t, comma negative cosine t, comma t, that would give us our helix. Okay, so you can kind of think about some of the things that you're comfortable with, familiar with, and how they're going to be represented by vector valued functions. Okay, so here's one. This is a simple parabola. It has no orientation. But what if we wanted to talk about something, like let's say we wanted to talk about a planet that was in orbit and maybe had a parabolic orbit, so it wasn't a planet, because then it wouldn't have an orbit if it was parabolic. But what if this was just like some piece of space matter that was traveling in this direction and then just getting shot off into space, maybe rotating around something that was right here that it was attracted to. So what if we wanted to write this thing as a vector valued function? Well, a lot of times we just choose a parameter. So what if we let x equal t? Okay, well then y would equal t squared plus 1, because x is t. So we substitute t in for x. So then our function for our parameter, our parametric function, would be r of t equals ti plus t squared plus 1 j. Or we could write that as r of t is t, comma, t squared plus 1. So that right there is a parabola, okay, that is represented as a vector valued function. Don't believe me? Just pop in some terms. T, and then r of t. Let's try 0, 2, negative 2. Let's try 0, 2, 4, 6. See what happens. Well, at 0, you get the vector 0, comma 1. Well, good. That's this one. Okay. At t equals 2, you get the vector 2, comma 5. That's that one. At 4, you get the vector 4, comma 17. That's that one. Okay, and you can just imagine that's what it's giving you. So just remember, this black vector valued function, you're graphing the endpoints of a bunch of vectors. Okay? But you'll find as we move on this chapter that it can be very helpful in how we kind of understand the physics of these moving particles. Okay, so do we always just let x equals t? I mean, that kind of seems like a waste of time. We're just kind of switching out one variable and adding another. No, the answer is no. So think about this one. What if we wanted to find a set of parametric equations that would represent the ellipse? So how could we do an ellipse? Well, letting x equals t on this one is not going to help us with a nice vector valued function for y. But what if we let x equal 2 times the sine of t? Well, I know that sine squared plus cosine squared equals 1. You can see why I picked the 2, because x squared is going to be 4 sine squared of t. And the 4 divided by 4 will cancel. So if I let y equal 3 times the cosine of t, then y squared is going to be 9 times this cosine squared of t. And sine squared plus cosine squared indeed does equal 1. So our r of t, and this is not unique. You could have came up with another totally different equation. For example, you could have let x equal cosine of t, which you're probably more used to, and let y equals sine. Let y equal sine. And it still would give you the exact same curve. Now what would be different would be your orientation would change. So now you can see, you can kind of play with your parameters to change the orientation to match whatever it is you're trying to represent. And so if we did let r of t equal 2 times the sine of t, comma 3 times the cosine of t, that vector valued function is going to give us an ellipse. Boom!